This is the current list of assignments. So 2.2, that's a new one I just posted today. That's a short one. That'll be due on Thursday next week, and the web assignments we have up to 2.2, and exam 2 is going to cover. So if you look at the syllabus, you'll see that we've got the rest of chapter 1 and all of chapter 2. So that's a good third of the material on the syllabus. So that'll be a good place to stop for the second exam. So I would say in about how many days is that? 1, 2, 3, 4. I'd say in about 2 weeks. I'll let you know for certain. Next week, at least a week ahead of time, when the exam will be.
Will 1.8 not be on the exam?
Oh, did I leave out 1.8? No, 1.8 will be on the exam. Thank you. 1.8. All right. So we finished lecturing on 1.8 yesterday. Let's look at some of the problems in there. All right, so 10, 12, 27 to 37 odd. 27 to 37 odd. Okay, so those are the main ones there. So with 31, we've got solve for x. 2x plus 1 bigger than or equal to 3. Absolute value 2x plus 1 bigger than or equal to 3. Remember the basic forms for absolute values, to how to eliminate them. When you have the absolute value of a is bigger than or equal to, well, we'll just say bigger than b. That means a is positive and bigger than b, or a is negative and less than negative b. So on a number line, looks like that. So here's b and negative b. B is a positive number, and you're looking at these kinds of intervals. And in the opposite, if you had absolute value a less than b, this means, and you can write it as one string of inequalities, negative b is less than a is less than b. So again, you've got minus b and b on your number line, but you're looking at the interval in between them. So once you eliminate absolute value signs from an inequality using one of these two things, then you can go further and solve from there. So here, this one is 2x plus 1 is bigger than 3. So this one requires two separate inequalities. 2x plus 1 is bigger than or equal to 3, or 2x plus 1, or 2x plus 1 is negative and is less than or equal to negative 3. So then you solve each one simultaneously. 2x is bigger than 3. Divide by 2. So x is bigger than 3 halves. This one, subtract 1 from each side. Divide by 2. And since we're dividing by 2 and 2 is positive, we don't flip the inequality, right? If we were dividing by a negative value in solving this linear inequality, then we'd have to flip the inequality sign around. So we get this, right? So x is bigger than or equal to 3/2. So since it's bigger than or equal to, you use the solid dot. And also x could be less than or equal to -2. So in interval notation, looks like that. Okay. Number 35. X minus 2 over 3 is less than 2. All right. So remember, the absolute value of A times B is absolute A, absolute B. Absolute value of A over B is absolute A over absolute B. And that's helpful here because when you do that, right, on the bottom you just have a 3, absolute value of 3, which you know, because you know the number 3 is positive already, is just 3. So this is x minus 2 over 3 is less than 2. Multiply both sides of the equation by 3. So x minus 2 is less than 6. Since 3 was a positive number, we didn't have to flip the inequality sign around. Okay. Here we have absolute value less than 6. So this is the situation in which you write it as one inline inequality like that to two simultaneous linear equalities. Minus 6 less than x minus 2 less than 6. And add 2 to each of the 3 parts of this string of inequalities, and you get minus 4 is less than x is less than 8. So the open-ended interval from minus 4 to 8. And which numbers did I assign in this section? Make sure we covered something similar to each of those. 16, 34, and 40. Oh, 16 was an equality. I forgot about those. So let's look at, well, there was a couple of those that we were assigned in the syllabus. 10, 12, 10 and 12. Oh, well, those are actually not so similar to 16. However, which one? I assigned 16 or 18? 16. Let's do 18, similar to 16. So number 18, so this is similar to number 16. So solve for x. 20 plus absolute 2x minus 4 equals 15. So this is not an inequality, but an equality. And in this case, if you have absolute A is equal to B, where B is positive, right, then absolute then either A is positive and is equal to B itself, or A is negative and it's equal to negative B. Right? So, similar to the situations with inequalities, but here you just have equality, one of two possible answers, right? So, what you want to do here is, oops, this one doesn't, did I copy it right? This one has no answer. All right, so no solution. All right, the absolute value of something is bigger than or equal to 0, so it can't be equal to -5. Or it can't be, yeah, it can't be equal to -5. That doesn't happen in 16, does it? No, in 16 it doesn't. Let's do one where there is a solution like that. 15. 15. So 18 is not similar to 16. Sorry. Number 15, similar to number 16. 4 minus 3x plus 6 equals 1. All right, solve for x. Okay, so what I would do is I would move the 3x plus 6 to the other side by adding that whole expression. You have to treat that absolute value expression as the thing you're solving for. Right, so I want to first express the absolute value expression to have it on its own on one side of the equation. All right, so this would leave me with 4 equals 1 plus absolute 3x plus 6. Now I can subtract 1 from each side, so 3 is equal to absolute 3x plus 6. Now I can apply this notion here. When absolute value of A is B, and B is positive, A is equal to B, or A is equal to negative B. So here we get 3x plus 6 is positive and it's equal to 3, or 3x plus 6 is negative and it's equal to negative 3. Right, going to give you it's going to give you two possible solutions. So this is 3x is minus 3, so x is minus 1. Here, 3x is equal to minus 9, so x is equal to minus 3. So two answers, minus 1 and minus 3. If you want, you can check them. All right, check your answers. Take the original equation. Right, and you can plug those values in. So plugging in x equal to minus 1, right, I have 4 minus the absolute value, minus 3 plus 6, equals 1. So 4 minus the absolute value of 3 equals 1. Absolute value of 3 is 3. So that checks out. And then the other one was x equal to minus 3. Right, so 4 minus the absolute value of, so if x is minus 3, this is minus 9 plus 6. So 4 minus 6 plus minus 9 plus 6 is minus 3. Absolute value of minus 3 is 3. So that checks out as well. Okay. I think that's all for this section. So we assigned 16, 34, 40. And yeah, you've solved everything. Well, we've given examples of things like those. All right. Oh, right. You guys handed in yesterday section 1.6. So, hopefully I'll get that graded for you. Today I'll work on getting the grading done today. That and the previous assignment. I sent assignment 1.2. I graded that one yesterday and sent you an email about it. So hopefully I'll get you 1.3 and 1.6 today, if not tomorrow. Alrighty. So section 2.1, it's on functions, an introduction to functions and what a function means. So a function written as f of x, like this. It's said f of x. Okay, and that's the way that's pronounced. So it's not multiplication when you write it like that, right? I mean, I know when we want to multiply like two things together, x and y, we write them like this sometimes, or we write it like that sometimes, or we write it like this sometimes, right? I mean, it's kind of similar to that, but that's not what this is. Okay, this is a function type notation. It has nothing to do with multiplication. All right, so a function written as f parentheses x, which is said f of x, has input value, or argument. It's also called the argument x, and that input is fed into the function to yield an output to yield an output, or value. Of the function. Okay, the input values are called domain values. And the output values are range values. So one way to visualize a function is like this, although it's not used that often in this type of context. So what context am I talking about here? This is a college algebra class or a pre-calculus class. So it's a class that's meant to prepare students for taking calculus, maybe statistics or something like that. It's a standard algebra track course. Standard sort of calculus differential equations track course, which runs through these topics in algebra that we're doing. And thinking of functions this way, or presenting functions this way, doesn't really ever come up in this context. But it's a useful thing to have in mind. So you have a domain values, a set of domain values, which these dots are. And then you got this set of range values. Okay, and every domain value goes to something in the range. Which something, you don't really know. Okay, but everything in the domain goes to something in the range. So let's give these things some names. We'll call this 1, 2, 3, 4, 5, 6, 7, and then we'll call these A, B, C, D, E. And these arrows represent function f. So a function that has this diagram, okay, what we're saying is that input 1, or domain value 1, goes to range value A. So this is written, we write, right, f of domain value 1, or input value 1, gives me output value A. So the value of the function is equal to A when the input is 1. The value of the function when the input is 2 is also A. The value of the function when the input is 3 is D. The value of the function when the input is 4 is B. The value of the function where the input is 5 is B. So this is an example. F of 6 is C. And f of 7 is E. Okay? So every domain value gets one range value. Maps to one range value. However, range values can come from multiple domain values. Right, so every domain value has one arrow going out, but the range values can have multiple arrows coming in. Right? So multiple arrows may come in, but out arrows you only got one. Now, most of the time we define functions, again, we don't use this kind of bubble diagram, this bubbles and arrows diagram kind of thing. That's for different, this sort of presentation of a function is more useful in other contexts, you know, that you don't really talk about in the standard mathematics track. If you're like a computer science student, then you will be introduced to, you know, other tracks of, you know, basic topics in mathematics, to go through other tracks, in particular in discrete mathematics. So, you know, there's this class called discrete math that that's made just for computer scientists. So that's a common, you know, alternative track that some students go through. All right, so the way we usually present functions, so most of the time, however, we will present functions using algebraic expressions, rational expressions, algebraic expressions, rational expressions, etc. So, for example, if we say, right, f of x is equal to, say, x squared plus 1, then this means that the value of the function f with input 3 is equal to 3 squared plus 1, which is 9 plus 1 is 10. All right, the value of f with input 0 is 0 squared plus 1, which is 1. The value of function f with input, say, -3 is -3 squared plus 1, which is, again, 10. Okay, etc., etc. So this is an algebraically defined function. Sometimes, rather than just plugging in just a simple number, for an algebraically defined function, we would like to define other algebraic expressions using that function. So, for example, let f of x be equal to, let's say, square root x plus 3, something like that. So f of x is defined algebraically using square root x plus 3. So let's evaluate these algebraic expressions using f. So suppose I wrote this, x over 2. F of x over 2. What does this mean? Okay, this means at every place where I see x, I will replace that with x over 2. So then this simply becomes x over 2 plus 3. Now, what's kind of confusing about that is, I'm using the same letter, x. Okay, but if you want, you could change that letter just to kind of, give yourself a different look at it. F of t over 2. So what this means is everywhere I see x, I will place t over 2. All right, so f of t over 2 is square root t over 2 plus 3. Which then, if you want to go back to the x, then you can. If it helps to change that letter, you can change the letter to some other letter and then come back to it. What does this mean? F of x squared. What would that mean? Right? Wherever you see x in the original definition of the function, replace x with x squared. Now what would I get?
Square root of x squared plus 3.
All right. How about this?
Square root of 2x plus 1.
Yeah, plus 1. Then, all right, you replace x with whatever is inside the parentheses here. Whatever the argument or input presented here, that input is placed wherever input x is shown. So 2x plus 1 is placed with the x. What's left? Now what's left?
Plus 3.
Plus 3, right. And you can simplify that, which would be 2x plus 4. So that's what you get when you plug things into the argument of the function, new things. What you could also do is you can do something like this: f of x over 2. So this is an algebraically defined. So this is an algebraic expression defined using f of x, but we're taking the entirety of f of x and dividing it by 2. So what would that look like? Right. Take the entirety of f of x, divide by 2. What would that look like? What algebraic expression is being spoken about here? What goes here? What's there?
Just the square root of x plus 3.
Right. F of x is the square root of x plus 3. And then I can divide that by 2. But sometimes you want to express things, some ideas abstractly, for any particular, any sort of not particular function f of x. So, right, I can plug x over 2 into the function, or I can divide the whole function by 2. Similarly, I can plug x squared into the function, or I can take the whole function and square it, which is going to be x plus 3 squared, right, which is just x plus 3. Well, how about this? 2 times f of x plus 1.
Two times the square root of x plus 3 plus 1.
Or you can do a lot of these things together. You can combine a lot of these ideas together by plugging in different things for f of x, plugging in different things for x, and then, having multiple expressions defined using f of x. So how about this? F of t plus 2 minus f of 2 over, f of t plus 2 minus f of 2 over t. What's that going to look like? F of t plus 2 minus, let's put a 1 there. F of t plus 1 minus f of 1 over t. Well, what is f of t plus 1, first of all? So replace argument x with t plus 1. And I get what? Square root of so if I put a t plus 1 here, I get the square root of t plus right, t plus 1 plus 3 minus f of 1. Well, that's square root 1 plus 3 over t. Simplifying this, square root t plus 4 minus square root 4, which is 2, over t. This type of expression with functions, this is central importance in calculus. So when you get there, you'll see what that's for. That's a way of defining this thing called the derivative. So hence the importance of this type of functional notation to calculus. Let's add another couple examples there. So let's say let f of x equal, now let's make a rational function. How about x over x squared minus 1, like this? So what is f of 4? Right, that's going to be 4 over 4 squared. Right, so that's 4 over 15. What is f of 0? Well, that's 0 over 0 minus 1. So that's 0 over minus 1. And that's fine. That's 0. 0 divided by whatever is 0. However, f of 1, that's 1 over 0, is undefined. What is f of t plus 1? Or let's not use the 1. F of t plus 2.
T plus 2 over t plus 2 squared minus 1.
Mm-hmm. And, we can put this bottom back into a standardized form. So that's t squared plus 4t plus 4 plus 1. So t squared plus 4t plus 5. How about that? F of t plus 2. F of t is what? Well, this is f of x. What's f of t? Just replace argument x everywhere you see it with t. And you get
t plus 2.
this is f of x, right here. And it's x over x squared plus 1. So f of t, replace argument x everywhere you see it in here with t. So you get what? T over
t squared minus 1.
T squared minus 1, and then plus 2. All right, so this is f of t, and this is plus 2. How about this one? F of t, t plus 2 minus f of 2 over t. Again, this thing called the difference quotient, which gets used in calculus for defining derivatives. Hence, we talk a little bit about it here, so it's not like a huge surprise when you first see it. Huge surprise when you see it next. That's it. All right, so f of t plus 2, well, we already did that one. That's this right here, right? So that's t plus 2 over t plus 2 squared minus 1. Minus, well, what's f of 2? 2 over 2 squared minus 1. The whole thing over, right, t. So this is f of t plus 2. This is f of 2, and that's just t. Right, f of t plus 2 minus f of 2 over t. And, that could be simplified, if we wanted to simplify it, which usually we do. We already did this one. It's t plus 2 over t squared plus 4t plus 5. This one is what, 2/3? Over t, and you could simplify further, but let's not do that now. All right, so, let's give those homework problems a go doing these things here. And you'll see, you should get the hang of it if you're not used to this sort of thing already. All right. So we were talking about the input values. Algebraically. Define functions. So we were talking about those input values being called domain values. So given an algebraically defined function, what is the domain? So usually the domain for an algebraically defined function, usually, that's often what we call it, is the largest set of real numbers for which the algebraic expression is defined. Right? The only time so far in all the algebraic things that we've looked at, the only problems that we really run into are dividing by 0 and trying to take the square root of a negative number. Okay, so we really haven't studied functions that that are problematic beyond that. Okay, so far, new paragraph. So for our purposes, well, so for the types of algebraic functions we've been looking at, all right, things defined with multiplication, division, square roots, and other types of exponentiation. The only issues that we pop up with that pop up for us are dividing by 0 and square roots of negative numbers. When trying to divide by 0, or take the square root, fourth root, sixth root, any even root of a negative number. You can take an odd root of a negative number, right? Like the cube root of negative 2, the cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is negative 8. It's just the square root of a negative number that's not defined, because when you multiply a number by itself, it's always positive. And when you multiply a number by itself an even number of times, it's always positive. If you do it an odd number of times, it's positive or negative, depending on whether the number you started with is positive or negative. Okay, so, for example, find the domain. Oh, so, right, we already talked about that. Find the domain for f of x equal to x squared over x squared minus x minus 6. Well, the only problem here is division by 0. Polynomials are just defined with addition and multiplication, and that's defined for all real numbers. Right? So the only issue here is division by 0. Right? Polynomials are defined for all real numbers because they are defined using only multiplication, addition, and subtraction. Nothing beyond that, right, with a polynomial. We don't even use division with a polynomial. I mean, unless you're having coefficients that are rational numbers, but that's fine. I mean, those are just numbers, rational numbers. The polynomial is defined using. I could have a half in front of that, but I mean that's a real number, so we don't worry about that. So, right, this is x squared is just x times x. That's just x. That's just 6, and then we're just subtracting these things, and this is just x times x. Okay, so that's always defined. The only problem here is get division by 0. Well, x squared minus x minus 6 equal to 0. All right, we know how to solve this. This factors. So we have x is equal to 3 or x is equal to minus 2. Right, so the domain for f of x is all real numbers x not equal to 3 and negative 2. So as long as the number that I'm plugging into that function is not 3 or negative 2, I'm good to go. It'll be defined, right? Because I can the only problem I get with division is, you know, the division by 0. How about this? It's very similar kind of example. X squared minus x minus 6. Well, what would I need for this to be defined? Find the domain. Right, so this requires is defined as long as what? X squared minus x minus 6 is what? What is necessary for this function to be defined? Again, you know, I mean, with square roots, you just don't want to take the square root of a negative number. You can take the square root of 0, though.
So as long as it's positive?
Like that? Or is there one other thing that we can say?
Or equal to.
Right, exactly. It's greater than or equal to 0. So this is x minus 3 times x plus 2, bigger than or equal to 0. Of course, we've been talking about these things. Here's the 3. Here's the negative 2. You test the intervals, and you'll get these. Right, so the domain is this, which is minus infinity to minus 2, union 3 to plus infinity. One more example using this. Find the domain. Oops, these are supposed to be solid dots here. Well, it's really close to this one, right? We need that the thing underneath the square root is bigger than or equal to 0. But, you know, with division, you just got to make sure you don't divide by 0. So over here, what do I need? So this is defined as long as, right? Well, we need x squared minus x minus 6 to be bigger than or equal to 0. But now, since we're dividing by that expression, it can't be what?
Can't be equal to 0.
Yeah, it can't be equal to 0 itself. So here it's just greater than 0. Right? And that's the exact same domain that we have here, except the minus 2 and the 3 aren't there. Right? Very, very similar examples, these three. I just used the same polynomial on the denominator, well, that same polynomial in 3 different ways, right? This function, the only problem is division by 0. So we found out where the denominator was 0. This one, square root of that same polynomial, we need the square root thing underneath the square root to be bigger than or equal to 0. You can take the square root of 0. The square root of 0. Square root of 0 is just 0, because 0 times 0 is 0. It's just the square root of a negative number that gets you in trouble, if you wanted to stick to the set of real numbers. And then, you know, same thing, except for taking the reciprocal of this expression, in which case, you know, the only things in the domain here that don't work out were the negative 2 and 3 themselves, because that's where you're equal to 0, and we don't want to divide by 0. Okay, these are the only problems that pop up for us so far with the functions we're looking at so far. There are going to be other functions later that will have other types of issues that go along with them. Okay, so that's it for section 2.1. We've only got 5 minutes to start section 2.2. Let us not. Let's just leave it at that for today then, okay? So we'll end here today. It's not enough time to really get into the next section so far. So have a good weekend, and I'll get the grading to you today and or tomorrow, okay? All right, everybody. Have a great day.